accessible times. So I will focus the rest of my lectures on this last case, the case of very long relaxation times, and not really touch upon the driven cases relevant to active matter or other kinds of situations when you want to drive your system externally. So after giving you this, sort of introduction to the problem, I went and derived, or at least sketched, the derivation of the Langevin equation from a microscopic point of view. And some of you noticed that there is a set of lectures that I just posted on the archive where this calculation is done in detail. So this is the reference here. And I also discussed a little bit the fact that this very general Langevin equation has the same structure that the equations that one calls dynamic mean field theory for these other systems or for glassy problems or for other kinds of problems in interaction have, only that in these cases here, there are terms that play the role of friction and noise correlations, which are not external, they are internal, and they have to be obtained in a in some self-consistent way. And of course, it's very difficult to do it exactly, so there are sort of approximations which are done. And if you want to make contact to what Eduardo was saying in the first lecture today, this morning, he was using this notation. Let me get the big one. The notation sigma of omega, no? The self-energy he was talking about. And it's not just a coincidence that we're using the same symbol. I introduced a sigma, capital sigma, also last week when I was telling you about this dynamic mean field theory equation. It has the same origin. So it is something that is telling you about the internal interactions in the problem. In Eduardo's case, okay, it was quantum. This doesn't matter so much. There was only a sigma, and there was not the D that I was showing last week. Why so? Because he was in equilibrium, while I'm not in equilibrium. So there's no obvious relation between friction and noise out of equilibrium for the internal part of the interactions. So this is why I have two. And he's stationary. I'm not going to be stationary. You will see that in a second, what I mean by that. But just to say that there is a parallel between what he was telling you about this morning, about the equation ruling the Green's function, and the dynamic mean field theory we are talking about in this context of classical dynamics. And then I talked about the existence or the coexistence of two classes of variables within the same system. So I gave you the example of looking at the momentum and the position of a single particle in the random walk situation, for example, just without a potential. And I was telling you that this one was equilibrating while this one, it was not. And, but they are part of the same system. So this is typical of what's going on in these problems. You can have coexistence of variables that behave in equilibrium and other ones that do not. And I also mentioned a little bit that if you focus on what happens with these variables, the ones that do not equilibrate, they can have themselves separation of time scales and behave ballistically for the mean square displacement for short time delays and diffusively for long time delays. So we will now go on with simple examples. So this example is also discussed in these lecture notes, and the one that I'm going to do now, right now, as well. So it's just to bring you to the complicated situations through little examples which are easy to understand. So the Langevin equations that I derived last week, they had acceleration. So they had it like this, and let me focus on one particle in one dimension to make it easy. But I also discussed the fact that the momentum equilibrates quickly for times which are longer than some t of v. I don't remember how I called it, but let's call it tx of v. That was equal to m over gamma naught. I remind you that I was working in the white noise limit. So white noise equation, and that gamma naught was the friction coefficient m, the mass of the particle. And if you look at times which are longer than this equilibration time for the velocity or for the momentum, you can basically forget about the momentum, because the momentum equilibrates to the Maxwell distribution. So in that limit, in the limit of these times being longer than this one, and any other time delay that you will like to focus on or study also be longer than that one, you can basically forget about the acceleration in the Langevin equation, go to what is called the overdamped limit. And just focus on the position. So the equation that you get in that limit for the white noise just has local friction in time. It has a noise which is delta correlated. This is because of the white noise bath. And you have a force. Now, let's imagine that I take a simple force. So let's imagine that I take a linear force like this one. So this is the problem of a particle in a harmonic well that we also discussed briefly last week. So there is a quadratic potential with a characteristic spring constant which I'm calling K. And this is the potential, right? And I center it at 0. OK? So now the equation to solve is very simple because it's linear in x as well. So x is here, and it's nowhere else. So it's a linear equation. And I'm going to add an external field. So this external field, I'll add it because I want to compute linear responses. What does it correspond to? It corresponds to adding to this potential a linear function in the position with a prefactor h. This is the field. And what it's doing is it's tilting a little bit the potential. So imagine that if h is positive, it's going to do something. Well, sorry, not good, my drawing. But OK, let me do it in a different way. To my harmonic potential, which was like that, I'm adding a linear potential. Let's do it like this. So this is the minus h x. So the equation is still solvable because it's still linear. So I can just solve it and find what is the position of my particle as a function of time for a given realization of the noise. So this is x naught e to the minus k over gamma naught t plus 1 over gamma naught OK, so you see how I do this? I just divide by gamma naught. Here, I divide by gamma naught all this. And you see that now the prefactor that accompanies the x that will decide for the exponential decay of the Green's function, if you wish, is this k over gamma naught. And this 1 over gamma naught comes because of there is 1 over gamma naught in front. So this is a solution in the presence of this little field. And for any realization of my noise that goes integrated from 0 to t times this Green's function. So this is like a Green function. OK, so now to make calculations a little bit simpler, let me assume that this is 0. So I just start my dynamics from 0 position, so from here. Just not to carry this term. But you see that already from here, I see that there is this characteristic time appearing here, appearing there, appearing in the Green's function. So I just can read already that there will be a characteristic time of x that goes like gamma naught over k, because I have to put it in the denominator, right, to make it a time. And I already see what I was telling you about last week, that this diverges if k goes to 0, or is finite if k is finite. Okay, I already see this from here. So this characteristic time will characterize all the properties of correlation functions, linear responses, observables I would like to measure about the motion of this particle. So which are the observables I would like to measure? So one, which is informative, is the correlation function between the position of the particle at a given time t and the position of the particle at another time t prime, t and t prime, average over the noise realizations. Recall what Eduardo was saying in the first lecture. He was correlating, what was his name, D, and another D in the quantum notation, right? And he was looking at symmetric correlations in time. Well, this is like the classical counterpart of what he was doing. And I will comment more about that in a second. So now, if I want to correlate these two observations of x at 2 times, and my notation will be here and later as well. This is initial time, this is t prime, and this is t. I always take t larger or equal than t prime, just for convenience. It's my notation. What do you want? Ah, oh, sorry. OK, thank you very much. Sorry. So I have to correlate this with that and take the average over the noise. And I will do it in the case where h is equal to 0. Okay, I focus on that case. In the case where I don't have this additional linear potential applied to the particle. So, OK, I do that. So I have twice this factor. So we'll have 1 over gamma naught squared. I will have the integral. So this, call it t second, because it's not the external one. I was just time of integration. Here I have t prime. Here I have t third. I have minus 1. Just let me call it t minus t second over that t of x. And then I have e minus t prime minus t third over the same t of x. And then I have two noises. But for the correlation of these two noises, I know that this is twice gamma naught kBt delta of 2 seconds minus 2/3. So this will cut one of the integrals. I have to be a little bit careful about, I was saying that I'm taking t larger than t prime, but this in principle is symmetric with respect to t and t prime, exchanging t and t prime. So I could also consider the other case. Anyway, this is a calculation to be done. You do the integral, and what you find is a result which will be proportional to kBt. You see, because it comes from here, the kBt. I will fix the prefactor later, because I don't remember it by heart. So you will have t plus t prime over t of x here minus e minus t minus t prime over t of x over there. And then let me put the signs and the constants correctly. So actually it's minus, plus, and there is decay here. Okay? So what you see is that if times are longer than these tx defined here, you can forget about this term, because it's exponentially decaying.
Letícia, just a question. I cannot read what you, because it changes the blackboard, so this
here.
is, yeah, it's t
minus. It doesn't write very well here.
It's the same term, but the one is plus, another is minus,
exactly.
right?
Here there's a minus.
Okay.
Yes. So this one is negligible. Drop it. You drop it in these limits, times which are longer than this characteristic time. So any of the two, say the shortest one, t prime, is longer than, yes? The external field I set to 0. So I'm correlating the positions of the particle in the absence of the external force. So it's not here, it's 0. Okay? And the correlations of the noise are here, are within the integral. And they will give me this delta function proportional to kBt, and then you cut the integrals, you finish the calculation, and you get this result. Okay? Yes?
Other questions?
It's gone, yes, because you see there is one from here. There were two prefactors in the denominator. One goes with that one, and the other one goes through the integration over time that remains because it's here. Okay? Okay, so in that limit, t prime larger than t of x, you just get this exponential decay as a function of the time difference. So I put it with a parenthesis. If I want to make the result symmetric in t and t prime, what will happen is that this is an absolute value. So let's put the absolute value to be well generic. Okay? So I get a correlation function. What do I have to read here over t of x? Huh? I have to read that it decays exponentially. So it decays fast with t minus t prime. And it is a function of t minus t prime only. Once I have dropped this term, because t prime became longer than this equilibration time, say that the equilibration time was there for the position, then it's what is called stationary. So a function of t minus t prime only, not of t plus t prime. The dependence on t plus t prime disappeared. So Eduardo also today said that when he defined his green function for the correlations of the d's, it was stationary, and that this could be proven. He was working in equilibrium. If I compare to my case, he was working for times which are longer than this equilibration time for the position, and I also get a stationary result. The stationary result is completely general, as he said, and it's indeed very easy to prove if, for example, if you work in the quantum case. Let me show it, because it's just really very simple. You can also do it classically, but it's even simpler quantum mechanically, and just to make contact with his lecture, let me do it that way. So imagine that you want to compute the correlation function in equilibrium. Now these angular brackets here means that you do an equilibrium average. And these are the Heisenberg operators, as he was defining. So this is the trace of what? Of E ht over h bar, A, E minus ht over h bar, and then you have E ht over h bar b hat, and now I change blackboard. E minus, this is t prime, this is t prime, E minus beta h hat. Okay? So here I'm saying that this is, okay, normalized by z if you wish, normalized. So this is the rho x, so it's the density operator a la Boltzmann in equilibrium at an even temperature beta, as he was saying. Now notice that because of the trace, I can move this here, and then I can move it here. Why so? Because the first is because of the trace, which is cyclic, remember. And the second one is because the h which is here is the same as the h which is there. So they commute. This is a necessary condition, that you have equilibrium with a given h and that you evolve with the same h. When you put it here, you notice that you can combine it with this other exponential, and you will have e minus h hat over h bar of t prime minus t. And here you combine these two, and you have e to the minus h hat of t minus t prime over h bar. And then you see the only places where time appears is here and here. And it's in the combination t minus t prime. So the result cannot depend on anything else than t minus t prime. So if you reached a situation in time when you reached the equilibrium density operator quantum mechanically or the equilibrium distribution function classically, then your correlation functions will be stationary. And this means that they depend on time differences only. I did it for correlations between two operators. You can do it because in the same way for correlations between any number of operators. And what this means, stationarity means, is that, I don't know, if you do A of t, B of t, C of t prime, t second, this will be the same as A of t plus delta, B of t plus delta, C of t plus delta, and so on and so forth if you have more operators. So you translate, sorry, t prime, t second. And this is t second. So you translate time by the same amount. So you translate this, that, and that one by the same amount delta, and the result should be the same. So this is also why stationarity is also called sometimes time translationally invariance, because you translate time by the same amount, and you get the same result. So in this sketch over here means that if I correlate between these two times, or if I correlate between these two times, where this distance is delta, and that distance is also delta, then I should get the same result. Okay? Good. So this is about what we get for the correlation function between two observables. I go back to the example now. Let me write it here. So this is the result that I get for this correlation function in the limit of the time, the shorted one, or well, both times, longer than the equilibration time for the position. And now I'm calling this Tx here equilibration time for the position. Because it's the time beyond which I get a stationarity. But is this sufficient to be sure that I'm in an equilibrium situation? So imagine that you have some experiment or numerical results. You measure a correlation function. You get a stationary result because you compare it, at different pairs of times like this, and you see that it doesn't depend, or it only depends on the time difference. Is this sufficient to be sure that you are in equilibrium if you don't know it? The answer is no, it's not sufficient, because you can have what are called non-equilibrium steady states, which are situations where your dynamics is stationary, but either the density operator in quantum or the distribution function in classical have not reached the Boltzmann distribution. And which is another measurement, which is finer in a sense, it's more delicate than just measuring correlation functions. Those are linear response functions. And this is the reason why I added this little field here to be able to compute a linear response function for my simple example and show you, its definition and what it looks like. So let me erase here. I keep that, yeah. Yes? I will tell you in a second. Okay. I will tell you in a second with an example.
So people, please ask in the microphone because it's being registered, and then no one can hear if you don't ask.
What Luis was asking is to explain why having a stationarity is not enough to ensure equilibration. So I told him that I will show it in a couple of minutes with an example. So let me first define the linear response function. This is a definition. So it's the variation of the expected value of the observable you look at, and here is the position, under the field with respect to having applied the field at a given instant t prime. It's like a strike that you give at t prime to your particle, and then you switch this perturbation off. So you see this quantity here, I have it already, so this is under the field. Let me use the same notation I was using. I have the H under the field. I can take the average over the noise first or after, it doesn't matter so much. The noise will disappear. I have to take the variation with respect to this H here at time t prime, so this will give me a delta function. So you see what I'm doing is I'm doing this. So like this, I jump. Here, in any case, I will get 0, and there I have this. So this variation gives me delta of t second minus t prime. This cuts the integral. And what is left is this, times the 1 over gamma naught. And you see here several features. So first feature is that I have to apply the perturbation before measuring, because otherwise I would get 0, right? If I was, for example, setting this to be a time which is before I kick my system, the system cannot respond. So this result is OK, but I have to combine it with a theta function. So it's like the retarded green function that Eduardo was talking about, because it's causal. So t has to be after t prime to get a non-trivial result. And the other thing I see is that I get, again, a stationary result. This is a function of t minus t prime only. Now, constrained by causality, but if I want to write it symmetrically with respect to the 2 times, I would have another theta function with the time reversed and so on. But let's assume that I'm at t larger than t prime, like in that setting over there, and this is the result. So the linear response that I get is also time translational invariant, is also decaying fast with the same characteristic time, the same tx, and it's stationary, okay, time translational invariant. Good. Yes?
So is there a hand-waving reason to explain why the linear response does not depend on h, but it still depends on k, given by both are in the potential?
Because this problem is too simple. It's very simple. So just what we would call bare green function you know, the one that corresponds to the differential operator. There are no interactions in this problem, right? So the bare green function is the linear response itself. And it doesn't depend on anything. It doesn't depend on h, as you said. It does not depend on h, but it depends on k. Exactly. It depends on the characteristic time. It's on the only thing that it can depend. Because it's the one that characterizes the decay of your green function. In other problems, it's not necessarily true what I'm telling you. If you had interactions and you had nonlinear terms in your Langevin equation, then you will have terms that depend on h, and you will have to take the h going to zero limit explicitly to get the linear part of the response. Here, this is not really necessary in this problem, because as you said, this doesn't depend on h. But it's special of this linear problem. Okay, so I have this linear response now. Let me write it here. So this is the correlation. And I also have the linear response, which is 1 over gamma naught e to the minus t prime over the tx times the theta function. So now I can say, OK, let me compare the two. Let me compare the two because I haven't learned much more about looking at the linear response independently from the correlation function. I just got the same relaxation time and also an exponential decay. So, you know, nothing very new. So let's try to compare the two. And the way in which I'm going to compare the two is through what is called the fluctuation-dissipation relation, which indeed compares linear responses to correlation functions, and that in equilibrium is model independent, and it only depends on temperature. You will see how for this example. Then it can be proven in general. So let me give you the statement and then tell you that you can check it. So if you compare the exponential decay of the linear response to the time derivative, this is the derivative with respect to the smallest time, let's say, of the correlation function that I wrote over there, you will see that the only thing that remains is 1 over kBt between the two. You can already sort of see it from here. I made a mistake, no, when I wrote here this. It's over k. I think I made a mistake, right? Yes, this is k. Sorry. That's k. So if you take the time derivative with respect to t prime here, you see what will happen. You will get this 1 over tx. 1 over tx will be such that it will cancel the k, and it will remain a 1 over gamma naught. That will be the gamma naught which is there. So this is, for this problem, is satisfied. But it turns out that this is satisfied, is valid. It's a theorem. So valid for all systems, classical systems. The quantum version is slightly different. Systems in equilibrium at temperature kBt, or and this can be proven in different ways. I'm not going to make the proof, not going to give you the proof because it would take a little bit of time, but you can find it in different places, and there are many reviews and so on and so forth. So you see, the interesting thing is that it doesn't depend on the potential. Here I just showed it in this trivial example of the harmonic oscillator, but it's valid for any kind of potential V of x, nonlinear, you know. The condition is that the system must have reached equilibrium with the Boltzmann distribution at this temperature. And the temperature appears here. Okay? And this turns out to be a much detailed property of equilibrium, because in those nests that I was telling you about, you can have stationarity of the correlation functions, stationarity of the linear response, but violation of this relation. And then you know you're out of equilibrium. So this has been used in different contexts as tests of equilibrium or as evidence for out of equilibrium. And it turns out that in certain out of equilibrium systems, with the slow dynamics, separation of time scales, and so on and so forth, how this is modified has a lot of information, tells you a lot about the behavior of the system. And it also is important to tell you already now that in those cases, this 1 over kBT, that it was the temperature of the bath, right? Is the temperature with which the system is of the environment with which the system is in context, it will be replaced by something, so non-equilibrium, let's put it this way, systems with slow dynamics, there will be a meaning to that in terms of effective temperatures that I hope to discuss a little bit in the rest of the talk today. Okay? Other questions here? Yes.
What I
say it again, please. I didn't hear. What do you have to do it quantum? Something very similar. So, for example, here, what you will do to compute a linear response is that at a given time, say t prime, you will modify your h.
I was referring to make to get the conclusion if the system thermalized.
That's the same conclusion. The only thing is that you don't have to compare to this relation between correlation and linear response, but it will be more complicated.
Oh, perfect.
The equilibrium FDT in quantum is a little bit more complicated than this, but you could say, okay, let me see if it works. If it works, I'm quite happy, and it's again even more evidence for equilibration of the sample. If it doesn't work, it's out of equilibrium. Yeah. Yes.
I have a question related to the, perhaps with the first part of the first lecture.
Yes.
Talking with Chris in this weekend, we are talking about, and I think that's why I'm connecting now. When you couple the bath and the system, you say, well, the function doesn't really matter. That was the answer that you gave.
The gamma, you mean?
No, the function that
the function that I couple to the noise, yes.
All those results holds if the function is such that you have longer range interactions, because now everything that you are telling us, it seems to me that is valid if you don't have very long, let's say, I don't know if you have an electronic system or all this keeps valid.
It depends what. I mean, of course, the functional forms of the correlations and linear responses that I'm showing are very specific to this very simple example. But the fact that you will have a stationarity and FDT in equilibrium, it doesn't depend on the potential at all. You will have it for any equilibrium system, as Eduardo was saying, and through this simple calculation over here. Okay. And to prove FDT is quite simple. It's simpler quantum mechanically than classically, because it also has to do with the periodicity of the trace. You prove it very simply, quantum mechanically. Then you can take the classical limit and get that expression over there. So stationarity and FDT are generic properties of equilibrium, whatever the system. The way you will break them out of equilibrium will depend on the system. So now I come to your question, Luis, and I make contact with what I said last week. So let me see what I erased. I will erase here. So last week I was telling you about coupling to baths and the fact that baths can be generic in the sense that they can have correlation of the noise and they can have associated frictions that induce memory. So let's have a look at this same oscillator, but now coupled to two baths. Erase here. Not to confuse you. Here. Sorry, I'm a little bit obsessive with cleaning the blackboards, so it takes some time. OK, so now imagine that I have that same problem, but I couple it to two baths. Two baths, each in equilibrium. But say that one is white, so just like the one I was using. It has some temperature, and it has some friction coefficient. And the other one, let me call it colored. So what this means is the gamma function that I was defining last week. I take it to be exponential, for example, with some time, characteristic time tau. And to make things well defined, I think I have to put some prefactor here. So let me put it proportional. It's to keep the correct units of this gamma, I should have something like a friction here. Well, I can put it. OK, let's put it. Gamma slow. Let's call it gamma slow. Why so? Because the white one had correlations which were delta functions. So if you wish, they are instantaneous. They decay super fast, like a delta function. This one instead decays with a characteristic time, which I can make long. I can tune it. It's a parameter. And it has this other bath, another temperature, T star. Okay? So each of the baths is in equilibrium, but they are different baths because of the temperature and because of the relaxation time that they all have. So we can have a look at the same equation, but of course there will be other terms appearing, right? Because as we did last week, let's call it this second, not to confuse you with the equals 2 minus k x plus psi plus eta. And let's say that eta is the noise of the second bath, is the noise, which I also take it to have 0 mean, but be correlated with this gamma function. OK, so the KBT star is the one that appears here. The gamma is the one that appears here for the correlations of this other noise. And this is associated friction coefficient. But now it's not a coefficient, it's a function. So there is a delay there. Fine, so this equation is still solvable because it's still linear in X. You see? So I can solve it. And I'm not going to do it explicitly, but you can do it if you wish. It's easier to do it going to Laplace because there is this 0 here. Anyway, there are ways to solve this equation. And what you will get, I'm going to give it to you in drawings. So for example, you can plot the correlation function. So this is just as before, x of t prime, where I average over both noises. I have to average over the white noise, and I have to average over the color noise. So I average over both. And imagine that this tau is quite large. I can tune it to be sufficiently large so that what I will see is that this correlation is still stationary for t prime larger than some t of x that may be more complicated than the one that I wrote you before. It may depend on tau, on gamma naught. I mean, it may depend on many things. But there will be a finite expression for tx that depends on the parameters of this more complicated problem. If I go beyond that time, the correlation is still stationary. And what I will see is I will see it decaying in 2 steps. I will see something like this. I'm not putting the scales of the axis. I don't want to discuss so much the functional form. It can be very complicated. But there will be one first decay. Controlled by the noise, which is fast. And there will be a second decay controlled by the other one. And there will be, if I choose my parameters adequately, a nice, separation between these two time scales. I can make them separate, and let me call Q the value of the correlation. This is the correlation at equal times where I start from. It goes to some Q, and then it decays further with a different functional form that is controlled by the second noise. So I insist, the dynamics is stationary. I get something like this if I solve the equations. Now, let's have a look at the linear response. I told you that there is this FDT that should apply to any problem in equilibrium. But now I have a problem with two temperatures. My bath is a complex bath that I can just not put together into one because it has pieces that decay in different time scales. Not only the noises are different, but the way in which this memory kernel behaves is completely different. In one case, it's delta, in the other case, is. So I cannot just put them together and say I have a single noise, a single bath at one temperature. I have two baths at different temperatures. So what should I put here? So the fact will be that this will be broken in this problem because I'm coupling to a complex bath. I cannot equilibrate to this simple bath. And how can I check that? This nice way to check it is to define what we call the integrated linear response. So you see what I do. I integrate the linear response over a time interval that goes from t prime to t. So this is like applying this perturbation, starting from here and going on for all times until my t. So it's like applying the field here, there. So I'm integrating the linear response over all the moments where I apply my field, and I measure at t. So this is my integrated linear response. If I compute it for this problem, what I will see is that it increases from 0, because if t is equal to t prime, it's 0. And it will increase, and I will draw it here as well. So they say that this is 0. It increases from 0. It does something like this. It also plateau-ish likes, and then it goes up. And let me call this plateau chi q. And the scale, well, my drawing is what it is, but the scale where this starts deviating from this plateau and the one that deviates from that is the same. It's the same time scale, which depends on the parameters of the problem and so on. It's a complicated expression. It's not needed to give it. So if I compare this to what I would have in the right-hand side here, so what would I have on the right-hand side? Well, some prefactor, which I don't know what it is, because I cannot put t nor t star, whatever. But I integrate this. Let me integrate that. I integrate this over the same time interval. And this is a total derivative. So this is c of tt minus c of t comma t prime. Proportional, let's say. But there is this thing which I don't know in the middle. And then there is the result of the integration. So now what I can do is I can say, well, OK, let me see. In this complicated problem I'm looking at, what happens with the comparison between the chi and this part here. So notice, the chi is a function of t minus t prime, say f chi of t minus t prime. And what I have here, OK, this is a constant. This one can show it's a constant. Doesn't depend on t. This is also a function of t minus t prime. Let's say fc of t minus t prime. or maybe call FC everything. So all of this is an FC of t minus t prime. Because this is a constant, that's t minus t prime. Everything is a function of t minus t prime. So I can just do a parametric construction where I put in this axis C of t minus t prime. Let me see how I write it. Yeah, C of t minus t prime. And I put on this axis chi of t minus t prime. Okay, if FDT were to hold, there would be a linear relation between this and this one. So let me write in red what is it if, well, this one is not visible. Let me get another. If FDT, okay, in equilibrium, so in the previous problem I told you about, that would be a relation like this, with a slope -1 over kBt. You see it from here. I integrate here, I get chi. I integrate there, I get this C of tt minus t naught with this prefactor. So it's a straight line with the slope -1 over kBt. But now, in this other problem, I don't get that. But what I get is very appealing, let's say. So what I get, let me erase this one. Oh, no, I don't erase it, but I make some space. What I get is something like this, and then something like that. So what is this? This is -1 over kBt, the temperature of the fast bath. And this here is -1 over kBt t star. And in my plot, I suppose that t star is larger than t. Otherwise, I would have gotten the slope in the other direction, right? And what is this value here? This is Q. And what is this value here? This is chi Q. So the crossover that I see in this representation as a function of time delays at this plateau and at that plateau, I see it in this parametric representation as sharp points, a sharp change with that separates these two straight lines like that. So let me say, here I'm writing C of 0. This is the point where t is equal to t prime. So this is C of 0, whatever is the correlation at equal times. Chi is 0 at equal times. So chi of 0 is 0 because I'm not integrating anything. So when I increase time delays, I move from this point, which is the one that corresponds to equal times, and I move in this direction by increasing time delay. So the correlation decreases, the integrated response increases, and then it changes its functional form, if you wish, of this parametric construction and becomes another straight line. So this is telling you that by coupling to this complex bath made of two different baths, I induce into the dynamics of a completely trivial problem, just a harmonic oscillator. I induce this separation of time scales. I have a separation of time scales because between what is here and what is there, and what is here and what is there. And the thermodynamic properties of the problem as well, because the dynamics occurs as if the system were in contact with a single bath at temperature T for short time distances, and another bath at temperature T star at those other time distances, yes. And of course, how this thing decays depends on tau. Tau plays a role on how this decays, but okay, that would be too much details. It's not necessary to discuss that here. So you see, I insist upon the fact that I have a stationarity for everything I can measure, but I don't have equilibrium because I have this chi of C relation, which doesn't have a single straight line at a single value of a temperature. It has two. And this behaves as equilibrium at T, if I look at time delays, which are here, but this is as at equilibrium at T star. Yes?
So can this picture still work if T star were, so I guess T star has to be less than T for this?
No, not necessarily. It can be higher. I'm giving you the ideal situation where the separation of timescales is, sufficient to see the two regimes, right? Yes. If tau is not sufficiently long, then of course the two regimes mix, and I wouldn't have the plateau.
No, but imagine you have long tau, but you'd have a T star such that the slope of the second line goes up. Yes.
Yes.
That's perfectly compatible. Okay.
Yes.
Thank you.
Yes, Caro.
Okay, so this is a very interesting way of seeing this tool, two decays in the correlation functions.
Yep.
It's a little bit weird to think about connecting to two baths, but I buy it, no problem.
Yeah.
But now, if I think about supercooled liquids in which you see those two timescale separations, I guess it's not what's happening, right? I mean, even if I think that I have a system in which these type of correlations in two time steps appears, let's say, naturally.
Exactly.
Do you have in mind that you could explain with this?
Yes, this is the game. This is the aim of the exercise. To tell you that in supercooled liquids, this is done internally. And while you are in the supercooled liquid phase, somehow the system arranges to have these two time scales. We will discuss the origin in a second, but it arranges to have two time scales, but both at the same temperature. Because in the supercooled liquid, you have FDT. So the T star and the T in the supercooled liquid are the same. But still you have, two relaxation times and fine with that. When you go into the glass, you have the two relaxation times, but you also have different temperatures. So the system arranges itself to have a different temperature for the slow degrees of freedom. And not only that, of course, there is breakdown of stationarity as well. Yeah, but right. That will come to that.
The glass, I would say, is not equilibrated. But
exactly.
I'm thinking about the equilibrated phase. Then you can think about having two baths already.
Yes, because recall, let's talk a little bit about the phenomenology of glasses. So when people talk about glasses, I want to keep that. Let's write it here. So you have your glass, a lot of particles. Let's say I'm in the supercooled liquid. So for those who don't know, the supercooled liquid is still in equilibrium with the bath, with the environment, but presents correlation functions that look like this, linear response functions that look like that. But if I do this construction, I get the blue curve. So supercooled liquid is the blue curve. And how do you figure out in a real space image what's going on? Well, remember that I was telling you, focus on one particle. So let me focus on this one. This one, it will make some vibrations. It will move around, within the cage. People talk about cages. So it's like the neighboring ones are making like a cage around it. And this orange one will move a little bit around there. And this will be the fast relaxation controlled by the external bath. So fast relax, controlled by T, the temperature of the bath, and the characteristic time of the bath. Then, if you let your time delay increase, if you compare what happens much later, this particle may have moved farther away and escape this little cage around it, be now surrounded by other particles, move a little bit further. And this corresponds to some structural relaxation where you don't have like a static picture of particles just vibrating around positions which are like a lattice, although that this lattice is distorted. It's not real. A lattice is amorphous, but they're just vibrating at short time differences. At longer time differences, things rearrange and change form. In the supercooled liquid, this second relaxation is slow. So you have this second decay and this second increase, but it's still controlled by the temperature of the bath because the system managed to equilibrate with the environment. So it's like a metastable situation in the sense that it didn't go to the crystal. It's a liquid when it should have been a crystal, but it's like a normal metastable state. So the slow relaxation is also controlled by T in the supercooled liquid. The real space image of the glass is very similar, only that the second relaxation is controlled by T star. And going back to Jaron's question, in the image of the glass that we have, we think that something like this happens, but just internally. This T star is larger than T because in preparations of glasses, one usually comes from the liquid and cools it down and lets it become a glass. But it comes from high temperature. It comes from an initial temperature, which is T0, which is much higher typically than the working temperature. So in a sense, the structure of the glass remembers the very disordered structure of the initial condition, at least at large scales. Large scales are long time delays. Long time delays are controlled by a temperature which is higher than the working temperature. If you were to do the opposite experiment, if you were to start from a crystal, this can be done in models, and it can be done also in certain numerical simulations. So you start from the crystal, and you heat it. So the initial T0 is smaller than the working temperature, because you equilibrate a crystal at T0, 0 temperature, let's say, if you can, if you know the crystalline structure, and then you heat it. You evolve at a higher temperature, always within the glassy phase, and what you get is this dotted straight line here, which is corresponding to a T star, which is smaller than T here. And this, again, can be interpreted as recalling the fact that the large structure was too ordered. So the T star is the characteristic T star of this very ordered configuration that you put initially is lower than the working temperature. Yes?
So if you start in the solid, you will have the other slope, but for all the way down up to 0, no? Why there will be the crossover still if you start?
Oh, because you heat it.
Okay.
So when you
Okay,
heat it, you want to equilibrate to T.
Okay, because T is coming already, equilibrating.
You want,
okay.
I mean, the T0 configuration that you put, the crystalline one, is not the good one at T, in
What
equilibrium
I mean,
at T.
so this with the break will be true for certain time in between the heating. I mean the heating process.
During the heating,
the heating process.
No,
because
I mean the heating you can do as fast as you want.
yeah.
So let me see. Let me clean. Here. So if you, this is the temperature of the bath, and this is time. So at time 0, when you cool, you come from a very high T0, and you cool it to some T, and you keep it constant, and say that T glass is somewhere here, okay? So you come from a very high temperature, and you cool, and then you keep the temperature constant. And in the other case, what you do is you start from a very low temperature, and then you heat it, say to the same, and you go to like that. So what will happen is that the perfect crystalline configuration, say, I don't know, something like this, that you had initially in the crystalline configuration will start breaking up a little bit because of temperature. So the things will start vibrating within the cage, and it's just like what happened here. It doesn't matter if this was ordered perfectly or disordered. The first part will follow the same straight line because it's controlled by the bath temperature, which is the same in my experiment. And then when I give time to distort everything, the dotted line remembers that, you know, the situation was like this. So I have to break this crystalline thing. And this is at a lower temperature than the working one. Yes?
Is this result caused because of the difference in temperature between the two baths, or because of the fact that one is white and the other one is color? If you had two white,
and then I know. Then if I have two white noises, I just mix the temperatures. It will be an average between the two temperatures with the corresponding gamma nodes, and I will have an effective temperature for the whole bath. I need to put two different time scales for the two baths to see this separation of time scales and to see this appearing.
Okay, so yeah. Could I think of a super cool liquid like something which is coupled to two different white
Not white, bath? Because I need to have this relaxation here is controlled by the toe, by the bath, which is at a has a longer time delay. There's a longer
I can have different temperatures, so different time scales in the two baths, even if they both are white. Will I see this double?
No, because if both
decay?
are white, the time scale of the two baths is the same. Is 0. So if I want to see the two relaxations, I need to have
not controlled by
a white and a colored.
Okay.
The white and the color could be at the same temperature, and then I will get the FDT blue line here. Or in the exercise, I put them at different temperatures, and I then see, and then I force this situation.
Okay.
Now, since this situation is observed in numerical simulations, you know, models, and so on, of glassy systems, remember that I was telling you that there was this dynamic mean field theory that represents the motion of these problems with Langevin equations, which have terms that come from the external bath, which are white, and terms that come from the internal interactions, which appear in the same way as a bath, but a bath self-induced. So this bath self-induced is out of equilibrium, and it has this other value of the temperature that it chooses itself, the system chooses it.
Okay, and one second thing. Will it be instructive to draw the correlation function and the chi function for the two separate baths if I had the system coupled to just the white noise one and the color
to compare,
on top of those to compare?
Yes, sure,
Is it possible to do that?
Yes, it's possible. So if you only have the white bath, you will have this kind of decay going on. If you had the slow one, well, it will be something like this other one for all the time delays, right? Yes?
The degree of freedom play a role here?
Say it again, what?
Degrees of freedom.
Of course. So I'm using this example of a single degree of freedom because it's already enough to show you all these features. Now, when I go to the case of the real macroscopic system, many body, and so on, what you have to think is that this degree of freedom is sort of the one that you have selected to write the dynamic mean field theory on. But it's just one among all the other ones. All the other ones, what we'll do is to create this gamma, which will be a function of the correlation of the linear response of the system itself, as I was saying last week, and the corresponding sigma that will be also a function of correlation and linear response. The explicit form of these gamma and sigma depends on the model that you will have. But many of these problems have this phenomenology, so you can discuss it in general terms. Say. Yeah.
This picture is valid for systems like supercooled liquids and gases, which
Yes.
never truly equilibrate. Because if they did, there should be a third regime controlled by T again, I guess.
Exactly, there will
Okay.
be. There will be another time relaxation time, sorry, much longer, presumably, that will depend on system size, where all this will be washed out, away, and they will eventually equilibrate. But this goes far away in time. Okay. Let me see what I wanted to tell you next. This I did. Okay, so now let me show you one problem, one real problem, where all these can be understood in terms of real space. And everything that I told you is very visual and very clear. So I have some, let me see if I can connect this. Where did I put it? Here. Oh, it's not this one, it's this one. If I can't connect, I'll draw, but if I can connect, it's better. Let's see if it recognizes my iPad. For the moment, it doesn't. Yeah, there it is. Great. So let's have a look at the problem, now a macroscopic problem, where what I have just told you is realized. And it's much better, it's much easier to visualize what I'm talking about. So the problem I'm going to tell you about is just the Ising model, okay? You get the classical Ising model in 2 dimensions. Those are the drawings over there. So let me keep this. So what I'm looking at is this problem, classical Ising spins, which take 2 values, plus or minus 1, black and white in the figures. And if I look at this problem in equilibrium with a bath at temperature T, I will have configurations, typical configurations of equilibrium, which look like that. So if T is infinity, I have as many, let me call it T naught, this one. If T naught goes to infinity, I have as many plus or minus 1s with probability a half. So each spin can be up or down with probability a half. There is nothing that distinguishes the 2 configurations. At the critical temperature, I see those structures which are critical and which are, domains of all sizes. So regions which are black, regions which are white, of all sizes, a lot of fluctuations, very disordered configuration. None of the 2 wins with respect to the other one. So if I compute, for example, the sum over I of Si, I get 0, apart from fluctuations that decay with n somehow. So in the limit of n going to infinity, there I get 0. And if I go below Tc, I get spontaneous symmetry breaking. So the system in equilibrium will choose one of the 2 configurations. Say that it chooses white here. So this sum will be equal to some value. Let me call it m, and I normalize by n. And this m, in that drawing, turns out to be m close to minus 1, but a little bit larger. So minus 1, I associate to white. Say that white is minus 1. So you see, it's almost everywhere -1, but there are some fluctuations. There are some black dots there that reduce a little bit, or increase in this case because it's negative, increase a little bit the equilibrium magnetization value, right? Because you know that the magnetization as a function of temperature is like this. In equilibrium, I'm in a negative branch, so I'm somewhere here. So it's not exactly -1, it's a little bit larger than -1 in that plot. So this is what I know about instantaneous configuration in equilibrium at infinite temperature, at the critical temperature, or below. Now, imagine that I compute the correlation function between two configurations of these systems at different times. So I do the same as I was doing before, but now it turns out that since I have a lot of variables, I compute this. This is the self-correlation because I'm correlating the spin at site I with the spin at site I as well, but at different times. And I want to look at how this quantity behaves as a function of time delay, and maybe as a function of the other time as well, because I don't know if this problem relaxes stationary or not. So if I take, say, the infinite temperature case, and I evolve it also at infinite temperature.
So, sorry, what's,
Yes.
What's the dynamics that you're using?
What's this, sorry?
Dynamic?
For easing problems, I can do Monte Carlo.
Okay,
I can
Metropolis.
also, sorry?
Metropolis.
Metropolis,
Okay.
yes, yeah. So I can also do Langevin with certain tricks, but okay, let's say that I do Monte Carlo. So if I start at T0 and evolve at T0, and T0 is infinite, let's say, then, of course, this correlation, now it's normalized to 1 at equal times because these are Ising spins. If I square them, it's 1. It's normalized to 1. So what we'll do, well, it will decay super fast. You know, there is no correlation time at infinite temperature, so I just plot it like this. It will be super fast decay to 0, and nothing very interesting. If I choose my initial condition, the critical temperature, so T0 equals to Tc, and evolve at Tc, then maybe you know there is what is called critical slowing down. So this exponential decay that I had at high temperatures, its relaxation time will increase. And what will happen is that if I plot in log-log scale, I will get T minus T prime to some power, 1 over Z, or I don't know, some power. Let's put the power. And not explicitate it, minus. And so it will decay slowly, like a power law. And this decay, I have to be careful, because here I say that I plot as a function of T minus T prime. I say that I start from equilibrium at Tc. So I'm sure the decay is stationary. So I'm sure I can do this, right? I'm sure I can suppose, and it's verified, that the correlation function decays on stationarily, so as a function of T minus T prime only. And it turns out to be that it decays like a power law, and this is what is called critical slowing down. But now imagine that I start from the white configuration. I start from the white configuration, I plot here, and what will happen is that it will decay to a plateau. What does this mean? It means that it will decay to m squared. It cannot decay further down, because the more these spins can decorrelate within this white configuration is through thermal fluctuations. I am in a symmetry-broken phase. I have already chosen to be in this branch, say, here at the cross. So I'm here. For this one doesn't exist because I'm taking n to infinity in my imagination. So for n going to infinity, the most that these configurations can decorrelate is magnetization square, because it's like breaking up these two. Each of them averages to m, and I have m squared. Notice that I'm not even writing an average over noise. I could write it average over Monte Carlo. But if I have n sufficiently large, it's not even necessary to do the average. If you do a single run, you will get what I'm telling you about. But n has to be very large. So I have the correlation which goes fast to this m squared. And if I do my chi of c construction, in the yellow curve, I will get the blue curve. In the pink, I will also get the blue curve. And in the white, I will also get the blue curve. Of course, with different values of the temperature, because the white is at infinite temperature, the pink is at Tc, the yellow is at some subcritical temperature. So the slope will be different, right? But I will only have one slope here, because I have equilibrium dynamics, because I assume I took an initial condition which was in equilibrium. Now, what happens if you do a quench, something like this? So you start from equilibrium at infinite temperature, at Tc, or below Tc. And you evolve at another temperature. So let's consider the quench. This is the last thing I will say. I guess I'm running out of time. Quench from T0 to T. And T, I make it smaller than Tc. So I repeat here. And let's consider the yellow case, which is the more interesting one for our purposes. The critical quench is also interesting, but let's forget about it. So I start from a T0, which is very high in temperature, very, very much. Let's write. So T0 is much higher than Tc, and I quench to T smaller than Tc. So this is the equivalent of the yellow curve. Only that what will happen is that it will decay the correlation in two steps. First, it will go to m squared. And then it will decay further, like in the plot over there. But this will be what I get when I choose some value of T prime, say 10 Monte Carlo steps. Then if I choose another value of T prime, I'll get another decay. T prime equals to 100 Monte Carlo steps. And then if I choose still another one, I have no more colors, OK? So still another one, I will get like this, and so on and so forth. So the first part is always the same, while the second part is different. And why is this so? Well, let me show it with a next slide here. So let's focus on the second line. Just show the second line. There it goes. So I start from an initial condition which is very disordered. So T0 here is much higher than Tc. So it's the paramagnetic configuration with zero magnetization, very small regions of both colors, but no big domains. As time goes on, so those plots are taken at different times. So say that the intermediate one is taken at 10 Monte Carlo steps, to say, and the last one at 100 Monte Carlo steps. So what is this system doing? What it's doing is trying to break the symmetry. So it's trying to choose one of these two branches. But the point is that somewhere it chooses this one, and somewhere else it chooses the other one. So here it's red, and here is white. And it does that locally. So locally, somewhere it decides to be white. Somewhere else it decides to be red. And in the course of time, these two regions grow to become more red and more white. But if your system size is large enough, none of them reaches the system size. And you always have a situation with zero magnetization. So in this plot, you're always here. This is the temperature at which I work. So you're always at zero magnetization. Parts are here, parts are there. They're larger, but they're both present at the same time. And then what does this correlation mean? This correlation means that if you look at time differences which are not very long, you're basically comparing the intermediate configuration, say, with itself a little bit later. So the only thing that could happen is some spins fluctuate within the domains, like in equilibrium. So you see this correlation to m squared. So here, just spins fluctuate within domains. And there is no domain wall motion. So the domain walls are the interfaces between the red and the white. So in this scale of times, the domain walls couldn't move. In this scale of times, the domain walls have moved. And you have been able to see the change between the intermediate and the last figure, for example, and so on and so forth. So this part is controlled by domain wall motion. Well, this is just like equilibrium fluctuations, nothing else. So this is the equivalent of what I was saying about the particles' vibrations in the image of the liquid or the glass. Well, this is the structural relaxation, where things really change, where the configuration changes massively or importantly. Now, I think it's time for me to stop. I will come back to this problem later on, next week, tomorrow. And this is what is called aging. So I will discuss more about aging tomorrow, which is a phenomenon of all these macroscopic out-of-equilibrium systems, which is not included in the oscillator I discussed before, but it's something new, something else that builds upon these macroscopic non-equilibrium problems.
Oh, thank you.
Thank you. So Letícia, you talk about this situation where we had two different relaxation times.
Yes.
Is it possible to have
more,
like a distribution of
yes.
many?
So for example, if you put a hierarchy of baths with different scales itself, and very separated so that you can distinguish them, then you can induce many. And there are models which they have these many internal relaxation times within them. And OK, one way to think about them is like this.
And then the relaxation, if you have like a very wide distribution, it probably is not, it has a different form of relaxation.
Exactly. You won't see all these plateaus, because if the plateaus get, collapse together, you will see something. But there are functional forms that can be written that can reproduce these things.
OK, thank you.
Yeah.
Just to make sure, so the condition for breaking FDT is we need both two different temperatures and two different agings, or just two different agings in the bath, it's enough to break?
No, because you can have two different relaxation times in the bath, but if the bath has only one temperature, then you will not break FDT.
So you are still in equilibrium.
You are still in equilibrium, right. So you can have a complex bath that has very complicated functional form for this gamma, but you just have one gamma with its temperature, and then you will be in equilibrium. But if you have pieces that respond to different temperatures, then you introduce these things. Yeah.
OK, thank you.
Yeah.
Other questions?
There's Luis here.
Thank you for the lecture. What will be the line in that plot for this particular system?
It's flat. So in the limit of very long times, T prime sufficiently long, you will get a flat line. So for this particular domain growth problem, and all other domain growth problems we know of, the T star is infinity. And it's not that we understand it very well why, but it turns out to be that. Yeah.
There's another question there.
Is there a time that time scale, for example, where taking the average over one bath is different? The order of taking you lose Markovianity? Maybe I'm wrong, but is there a time at which taking the average over the different noises that we have?
Yes.
Is different taking the order like eta first and then xi or the other way around?
No, for that problem, no, it doesn't matter.
Okay.
No, yeah.
I still have one question.
Yes.
So just be clear, the first part, when you draw the yellow line, means that you are taking already an equilibrated situation, and then you don't observe the second one.
And then you don't observe the second one. While if you start from a completely disordered initial condition, you first feel like if you were in equilibrium, but then you realize that you're not, because the walls move.
Let me just go follow up with Eduardo's questions. I don't know if you know the description, I think it's by Edgar, perhaps, I don't know, I don't remember exactly, but someone was proposing that the heterogeneities in the supercooled liquid phase, or in glasses perhaps, could come from the fact that you have different baths. Now I see in this way. I mean, is it, I don't know, I don't remember the person saying that it was different baths, but it was clearly, I know, some regions would have exponential relaxations and others would have a different relaxation times. And
yes, sure. You will have different relaxation times in different regions. Some regions could be fast and behave, well, grosso modo, let's say, like these ones. Yeah. Some other regions could be so blocked that they will behave like those, and something in the middle. But there is nothing forever for those regions. Yeah. They're not eternal. They're not, they will change because everything is moving. So during a certain time window, a region can be very fast, but then it will be blocked, and so on and so forth. So there are studies and a lot of ideas about how to characterize the distribution of relaxation times in space. And then we have with Claudio Chamon, your compatriot, a lot of ideas about how to characterize what happens with the temperatures for those regions. But okay, I don't have time to discuss.
Okay, no, it's interesting just to know. Okay, are there other questions? Okay, if not, let's thank Letícia again.
Thank you.
And we need to be here at 2 for the flag.